Okay, so this is an example of a screencast similar to how you might submit a standard for assessment. I'll include a few things that you wouldn't necessarily do it because this is coming out of context. Right here, this is the problem that we're actually going to be solving. You would normally have to restate the problem if it's coming from something that I posted or is coming from the textbook. So in this case, though, we're doing a problem that is straight out of Fundamentals of Physics 1. That's Physics 151. In the problem, we've got an ice cube that's set to slide frictionlessly down this ramp, and at the bottom it hits this loop-to-loop that's got a radius r. And the question is, at what height h should we start the ice cube so that it just barely makes it around through this loop? And there's some additional information about it right here, and some hints, and so on. So now getting to what it would look like when you actually submit a standard for assessment. I'm going to ask you to include your name, even though this will be originating as an email notification from you or a link to your YouTube channel. This will just help me keep track of what I'm looking at. Include the standard number, and there may be more than one standard that the problem corresponds to, and also the problem that you're solving. So in this particular example right here, there are two main ideas that are key to solving the problem. First one is we can use the concept of conservation of energy. So in this case, we're going to have a change in kinetic energy that brings about a change in potential energy. So specifically, a decrease in potential energy will lead to an increase in kinetic energy. This is just a version of the work energy theorem. And we have specific starting conditions. We know the ice cube is starting from rest, and it's starting at some height h, which we eventually want to find the value of h in terms of other parameters. So the second main concept that we have to use is the fact that in the loop is a circle, and so in order to move in a circle, we need to have a centripetal force. In order for the ice cube to just barely make it through there at the top of the loop, that force is coming exclusively from the force of gravity. If the ice cube were to be going a little bit faster than it needed to, then you'd be getting it from both the normal force from the structure of the track and also the force of gravity. But because we're just barely making it through, there's zero normal force. The ice cube's just barely touching the loop, and it's just gravity that's making it curve around in a circle at the very, very top. So we can write in the values of each of these two forces. The force of gravity is just mg, and the centripetal force is always mv squared over the radius of the turn. Now we can do just a little bit of algebra and solve for v squared in terms of the other parameters here. I'm solving for v squared instead of just v because I know later on I'm going to be using kinetic energy, which involves the v squared. So I might as well just save it that way to plug it in. That's just a little bit of a convenience. So plugging that in right here to find our change in kinetic energy. Well, we know our initial kinetic energy is 0, so the change in kinetic energy is just going to be given by the final kinetic energy. So that's 1/2 mv squared, where v is the speed at the top of the loop there. But hey, we just had v squared right here, so we can plug in from equation 4 and write that as now the change in kinetic energy is 1/2 mgr. A few other things now. So we have the kinetic energy, so let's turn and look at the potential energy, the other part of equation 1. So potential energy, in order to find that, we have to find out the change in height. Change in height is just the final minus initial. The initial height is h. The final height is the diameter of the loop, so that's 2 times r. And so the change in potential energy is going to be the change in mgy. M and g stay constant, so that's just mg times the change in y. We have it, change in y up here. We plug that in to get this expression right here. So now we can plug into equation 1 and equate our delta k and our delta u, plugging our delta k in from equation 5 and our delta u from equation 7. We get this expression. Now it just takes a little bit of algebra, and we can solve to find that the initial height of 2.5 times the radius will be what it's required to just barely make it around the loop.